Hi, everyone. Welcome to the fifth edition of the Future of Electrification Conference. My name is Barbara Veiga. I'm a digital marketing manager at Delta Q Technologies, and I'm very happy to be hosting this session with you today. We are about to dive into one of the most exciting topics shaping the future of our industry, the next generation of charging systems and the shift toward high powered, high voltage design. To guide us through it, I'm very pleased to introduce our speaker, Murad Shergi, Senior Product Manager at Delta Q Technologies. But before we get started, I would like to share a few notes. First, this session is being recorded and will be available to watch on demand after the conference. And if you have any questions during the session, please feel free to use the Q&A tab located on the right side of your screen. All questions are sent privately, and we'll do our best to answer as many as we can at the end of the session. We are very excited to have you here today, and I have no doubt this is going to be an insightful and inspiring conversation. Murad, thank you for joining us. The stage is yours.
Thank you, Barbara. Good morning, good afternoon, everyone, and welcome to this session. I'll share my screen and we can start the presentation. In today's session, we will talk about high voltage and high power applications in off-road vehicles, and we will start to looking at some of the trends in the industry. We will then look at high voltage adoption, drivers, benefits, hurdles. Then we will look at comparing the different voltage levels that are commonly used in the industry, as well as charging solutions. We'll talk a little bit about the transition from 400 volts to 800 volt systems. And then we will look at some of the solutions that are provided in industry, such as the one provided by the Zappi Group. And in particular, we focus more on onboard battery chargings for high voltage, and we'll finish up with a few key takeaways. So before moving to the presentation, let's take a moment to actually define some of the terminology related to voltages. In the industry, there is no general standardization. So every industry uses different levels, different terminologies. But for the purpose of this presentation and in the context of electric vehicles, we will define the drivetrain DC voltages levels as either low voltage, which will include the traditional safety extra low voltages, which are voltages below 60 volts, that are commonly used in light duty mobility, as well as industrial vehicles, as well as voltages below 120 volts that are used for heavy duty mobility, as well as industrial vehicles. Then, when we talk about high voltage, we mean voltages higher than 130, 140 volts, which are typically fall into two ranges. One is 400 volts, with voltages ranging from 300 to 500 volts, commonly used for automotive, as well as power DC machines. And then there is a little bit higher voltages, which is the range of 600 to 900 volts. That is more and more used for advanced electric vehicles, as well as heavy duty industrial vehicles. In the different major shows, industry major shows, such as Agritechnica and Conexpo, they provide a good insight into the off-road vehicle electrification. These shows demonstrate that electrification is rapidly maturing from experimental prototypes into mainstream product lineups, as evidenced by the number of electric product lines that are exhibited in these major trade shows. Most electrified equipment have been compact equipment featuring low voltage powertrain. However, in the past couple of years, this trend is reversing as we see more and more medium to large equipment being electrified and more adoption of high power, and high voltage powertrains. For example, we did a survey of the Agritechnica 2025, November 2025, and there were a total of 20, at least 29 electric vehicle models exhibited in these trade shows. And as we can see, the tractors are featuring actually high voltage powertrains as well as the feed mixers. Low voltage is still very present in compact tractors as well as still as other equipment, as telehandlers, loaders, excavators, and more specifically into the agriculture robot. But high voltage is becoming more and more dominant in the larger machines. If we look at um, uh, Conexpo, so we have tracked actually over the last three editions the number of vehicles that are exhibited. And as you can see, the number of electrical vehicles have been increasing, uh, and reaching a peak in 2023. In 2025, there was a little bit of softening of the numbers of vehicles exhibited due to the global conditions uh, that we are going through. However, the high voltage numbers, the high voltage vehicles that are exhibited in terms of percentage have been growing from 20% of the vehicle exhibited in 2020 to now 48% in the last exhibition that happened uh, last month. So a trend, like a more and more in off-road machinery, we see a trend toward high voltage systems. In construction, like construction and agriculture have been particularly with electrification uh, have been particularly trending towards higher and higher voltages. So in the construction equipment, for example, we look at machines such as excavators, loaders, backhoes, compactors, and in the agriculture, the main uh, the main vehicle used there are the agricultural tractors, but we do also see electrification with high voltage for feed mixers and combined. For example, last year there was like the first ever hybrid combine that was exhibited by Zoomlion at Agritechnica 2025. We do see another interesting emerging trend in the industry in traditional industries such as the material handling and the mobile elevated work platforms, MEWP. These two segments particularly have been very electrified. As a matter of fact, the electrification penetration compared to combustion engines is reaching like more than 85% in material handling and maybe 75% in the elevated work platform. And this two segments have been heavy user of low voltage systems with voltage ranges from 24, 36, 48, and 80 volt powertrains. However, what we have observed very recently is that many OEMs are adopting high voltage powertrains, particularly 400 volts platforms for applications such as high capacity forklifts in material handling, telehandlers, and even in large bombs, large elevated work platforms that are called bombs. The low voltage systems that are currently very mature have inherent limitations when being used on board mid and large size equipment. These limitations include that the vehicle cannot use low voltage vehicles cannot use DC fast charging uh, like from a traditional uh, electric vehicle charging station. They cannot like use DC fast charging. Only EC charging is available. Additionally, the current limits will be like a reach limits around the 500 amperes, so that more current would be very difficult to implement. as well. And this is due to actually to the limits of the conductor side that becomes very impractical beyond 500 amps. With the increase in power, the battery packs becomes bigger and bigger, and there are challenges with cooling the batteries and as well as other parts of the system, and heat dissipation become a major problem with low voltage. That's why many OEMs and applications are opting to go to high voltage powertrains. These high voltage powertrains offer the advantage of enabling higher power output. Indeed, the high voltage enable higher motor power outputs, narrowing the gap with traditional diesel engine in heavy duty machinery. Second benefit is that the current is lowered in intensity. So because we are increasing the voltage, then we can reduce the current, uh, like all still to get the same power, but also enabling a higher efficient energy transfers. Um, the high voltage systems are typically 3 to 6 times uh, higher in efficiency compared to traditional hydraulic systems in specific applications. Fast charging capabilities are also enabled, especially when using DC charging. And now with the emerging of even higher voltages at the 800 volt systems, then we can charge batteries to rates up to 4 times the capacity of the battery, which enable to actually charge the full battery in times as low as 15 or 20 minutes. All these factors uh, enable that the total weight of the vehicle is reduced because of using thinner cables, smaller components, and light overall systems. So this will allow actually for maximizing the payload capacity for this heavy duty equipment. However, the high voltage powertrain systems introduce another set of hurdles for uh, off-highway vehicle OEMs. These hurdles include, for example, the increase in component costs due to the usage of high voltage components, particularly silicon carbide semiconductors. They are uh, more expensive than low voltage. Thermal management becomes another major issue as high power electronics requires sophisticated cooling systems, which in most cases use liquid cooling for for different uh, systems, and as well as designing radiators and pumps that can handle these high thermal loads while surviving high vibration environments is a major engineering task. Safety and insulations is another important consideration. With high voltage cabling and components require increased insulation and stricter safety standards to ensure operator safety. The other issue is that the component supply is quite limited. So although high voltage systems are very mature in automotive applications, off-highway OEM face a challenge because of the lower volumes of the systems and the customization that is required for the system, putting them at the back of the lineup when when trying to use the latest power electronics or the latest power systems. The last important consideration is fast charging infrastructure that is lagging quite behind. Although in the automotive sector, there is huge deployment of fast charging stations all over, but this deployment is concentrated in high density urban areas like malls, like shopping centers, or offices. But not a lot of infrastructure is available in newer construction site or in the suburbs or in remote area. So bringing a very high power to a remote job site requires maybe using sophisticated mobile battery storage containers or massive grid upgrades. So uh, we are talking about these different voltages. This table summarize some of the main aspects of the different voltage level and compare them together. So if we look at the 60-volt systems or the 120-volt systems or 400 or 900 or even the emerging 1400 volts, that is a technology that is started. There is differences in terms of safety, silicon technology available, the availability of component and supply, as well as fast charging application. So the advantage, the big advantage about low voltage systems, especially the below 60 volt, is that they are very safe. They don't require uh, a lot of production or no production at all, actually, on the vehicle. And another advantage is that this vehicle could be maintained and repaired in the aftermarket by regular mechanics, while anything above 60 volts require that the vehicle will be maintained by an AV, an electrical vehicle specialized shops, which means a much higher cost of repairing this type of equipment. But the counterpart is that the more you go into higher voltages, you are enabling much faster uh, charging. So when looking at EC systems, basically for the systems that are below 120 volt DC uh, powertrains, then we can achieve like up to 22 kilowatts of charging. On 400 systems, it's easy to actually grow that to 43 kilowatts for AC charging and up to 200 kilowatts with DC charging. When you move the voltages to the levels of 600 and 800 volts, then the charging could be as high as 400 kilowatts. And even with this using liquid cool, we can even reach the megawatt limits. Emerging technologies, which is actually even higher voltage, are still in their infancy, but there is talks about 1400 or 1200 nominal voltages on this system. When you look at another aspect to important, we're actually looking at different voltage levels is the hazard and safety related topics related to DC voltage. And one good source for understanding these differences is the international standard IEC 60479-1, which actually looking at and particularly looking at the DC current. When you look at we look at DC current and you translate that to voltage levels, so this is a little bit of summary of what it entails. So for systems that are below 60 volts and that are considered in the industry as safety extra low voltages, the current typically stays below the current that could flow through a body, through body if like somebody touches live wires are typically below 2500 milliamps. So the like somebody can feel the live powers. However, there is no physiological effects, and that's why actually there is no safety protection that are required. When you go move a little bit higher to basically below 120 volts, the sensation become a little bit stronger, and then the person might have involuntary muscular contraction. But at this level, even like with the flow of current, there is no organic damage or no risk of ventricular defibrillation that could happen. So in these systems, there is like there should be extra production, but the current interruption mechanism are not necessary. When we go to the higher voltage, basically be above 120 volts, then currents up to 500 milliamps can flow to to the body. However, if what's important is actually not just like the current, but also the duration of this current flowing. So if we, the current are interrupted within 20 milliseconds, there is no organic damage, and there is a lower risk of ventricular fibrillation. So in these cases, a fault interrupting a fault current interrupting mechanism is required to actually ensure safety. For systems above 400 volts, the currents are much higher, and the risks of pathological effects will occur, such as cardiac arrest or brain arrest or burning. And also ventricular fibrillation risks are very high. That's why actually in the system, they all the electric parts have uh, uh, to be completely isolated, and that's why actually the importance of testing, not only during the design but continuously on the vehicle, testing the insulation to ensure that there is no damage or breakage of the insulation of the different components. So when looking at implementing high voltage systems, there are some considerations that need to be implemented, such as, and those are safety measures, such as HVRL, which is high voltage interlock loop, which is a dedicated low voltage circuit that's verified that all high voltage components are properly connected and cutting power if a connector is compromised. The second mechanism is the manual safety disconnect, MSD, which is a physical user-operated breaker in high voltage battery systems, like that are used like for maintenance during maintenance to ensure safety. The other device is the insulation monitoring devices that constantly should monitor the insulation failures between the high voltage parts and the chassis. The cabling as well as the connectors in these applications need to be provided with a different color, typically orange, to warn people that actually it's high voltage, as well as it requires double insulation during for the wiring and the connectors, as well as like the necessity of using specialized fuses and contactors that are DC rated and that are high speed, like they open very quickly to break the current, and as well as reduce the risks of arcing. And this is especially important in case of an accident or a crash. The big benefit actually of using high voltage systems, in addition to actually reducing the weight and the current, is being able to benefit from DC fast charging. So there are different levels, but actually for the purpose of the mid-size and large equipment, level 3, mode 3 and mode 4 are the one that are mostly used, and they use all these systems use the electric vehicles charging stations that are also being used in off-road machinery and with construction side or agricultural field, etc. Mode 3 is easy charging, and it enables uh, currents up to 22 kilowatts. When we go to actually mode 4, which is DC charging, so that allows for much higher uh, charging, going up to 300 or 400 uh, kilowatts, and that charge machines very fast. So comparing the different type of current and installation. So this is a summary of the four levels and enabling to see what are, for example, the DC charging currents that are involved. So, for example, if you look at level 1, which is plugging directly a device to an AC outlet, the maximum we can get is maybe 20 to 35 amps. But as we move like to DC uh, charging, we're talking about 300 amps up to 1500 amps of power. So That's some examples actually of the systems, of the connector systems, as well as different modes to charge the vehicle. So there is a variety depending on the application and the needs. A lot of the systems that are being deployed for off-road machinery use 400 powertrain. So this 400 volt architecture is has been the norm on on automotive electric vehicles, and it's transiting to off-road vehicles. So, so it offer lower cost uh, and design complexity versus even higher voltages. Components are relatively available for for the powertrain. Onboard chargers are typically, like that are supported in this field, are from typically from 3 kilowatts to 11 kilowatts, with 6 kilowatts being one of the most used charging levels. DC fast charging is supported and allows typically up to 50 kilowatts of charging. And there is significant deployment of the AC and DC fast charging infrastructure and charging station. So it's one that is actually very highly used in off-road equipment. But as the electrification is moving towards larger and more heavy-duty equipment, many OEMs are working on transitioning from 400 volts to 800 volts. So this transition, what does allow it allows for higher outputs, high power output, because like the higher voltages allows electric motors and powertrain components to deliver more power consist- consistently, supporting heavy loads and improve acceleration. The second aspect is that this transition to 800 volts significantly reduce charging times. So, for example, you can achieve 80% charging in less than 20 minutes on your system. So, this is 3 times faster than what our 400 volt battery can support. And, uh, and we can do 2 times the power while using the same cables or same gauge of cables that are used in 400 system, but still achieve twice the charging, reducing downtime the machine that stays while it's charging and enabling fast charging systems. The third aspect is actually the conductors could be reduced, like they could be reduced, saving space and improving, and this, which is the fourth aspect, improving the overall system efficiency. In many systems, what's another advantage is actually, for example, if you are doing 100 or 200 kilowatt charging with a 400 volt system, you may need actually cooling the AC cables. However, if you move to 800 volts, the current is reduced and you can use normal cables without cooling them, so that simplify the system as well as reduce costs. All these factors together lead to a higher sustainability for this electrical equipment, reducing battery sizes and lowering the overall weight and size of the equipment, and increasing the the range of the vehicle as well as the um, the autonomy of the vehicle. Almost all uh, uh, with almost all the OEM considering higher voltage are usually today using 600 to 700 volt electrical systems. So they are below the 800 volts because actually the semiconductors as well as cables as well as different devices are not yet widely available at the 800 volt level. So what you see a lot of equipment is in the 600, 650, 700 volts. But we do see that in maybe 3 to 4 years, there will be more systems to actually 800 volt systems with a peak voltage reaching up to 900 volts. So with the 800 volt systems, there is a need for um, uh, more safety to be implemented and different systems that are not familiar to OEM that are using either low voltage today or 400 volts. So systems like, for example, the pre-charge that limits the inrush current from moving to the power system when it's turned on, which otherwise would cause a lot of damage or requires actually over engineering the equipment. Uh, bleed, bleed off resistors also help with safety as they bleed off any voltage which may remain in the system even after disconnecting it due to the high level of capacitance that is typically found in high voltage systems. The high voltage systems are very noisy environments. Uh, so there is a need for high performance galvanic isolation to ensure safe and reliable operation. Often, the clippage distances and insulation resistance need to be doubled compared to 400 volts. And in particular, there is a need to develop and producing a class of 800 AV cable for properly handling up to 1000 volt peaks. One of the major challenges for high voltage systems lies in continuously monitoring the insulation faults or losses of isolation uh, than causing early interruption. So causes for insulation faults in normal operation can be, for example, contamination, storm, humidity, faulty connectors, or mechanical influence. AC and DC leakage current sensors need to be designed to monitor the resistance of conductors and continually measuring and analyzing the residual and fault current. There is an additional thing is that there are systems that need to be evaluating the thermal and electrical stress on the insulation system and the need for OEM to properly select materials for longevity and compatibility with other elements in the system. Finally, due to the high switching frequency and elevated voltage and current, there is an increase of electromagnetic interference in high voltage system compared to lower voltages one. AMC components and filters help maintain the correct operation of the onboard communication networks as well as the different as well as different equipment. So, after we discuss a little bit the trends and the technical and engineering aspect of high voltage vehicles, we take a quick look at what are the supply equipment that are available, and particularly we look at, as an example, to the ZAPI group and what how it's enabling the electrification of off-road machinery. So the ZAPI group is advantage of ZAPI Group is to provide an industry expertise as well as it acts as a partner in the electrification journey with providing all components of an electric powertrain. The company have a global presence and it offer global service and quality management throughout the world. Recently, the ZAPI Group have launched several components that are catered towards high voltage systems. We enumerate a few of those. There is the product line ACH3, which is a versatile high performance inverter portfolio. IMI, which is a permanent magnet motors with integrated inverters. DC C3, which is a rugged DC converter to convert either like the 400 or 800 volt to 12 or 24 volt. The group also have released several um, onboard chargers at the 7.2 kilowatts and 22 kilowatts, which we actually will look at in the next slides. The the group also has capabilities to actually integrate the different components to provide a turnkey system. And this is an example of a system that was integrated by the ZAPI group 4E consulting company, and that integrate the different components group into a high voltage powertrain. When we look at particularly the onboard chargers for off-road vehicles, this is the general requirements are needed. So we needed power from 6.6 to 44 kilowatts, single phase and three phase. The voltages ranges either in the 400 volts or 800 volts, which range from 500 to 900. The charger needs to support like directly do the conversion from AC to DC, but as well as support DC fast charging. Um, and it has to have like the safety, reliability, uh, necessary. The chargers need to be compact because actually not to take too much space, liquid cool, high ingress protection, and shock and vibration, and it has also the necessary regulatory approval, EMC and EMI. So these are some of the aspects that OEM should consider when looking at chargers. The Delta Q Technologies have announced recently a 7.2 kilowatt onboard charger that is available both at the 400 volt and 800 volt ranges. And the interesting part about this one is, like, beside being compact, is actually incorporate a 1 kilowatt DC-DC converter to provide auxiliary power. It allows to actually interface with every charging station for AC charging, as well uh, as well as support DC charging with, like, for example, it has the PLC communication required to interface with DC fast charging. Another product that is also announced is a 22 kilowatt onboard charger, similar to 7.2 kilowatt, but this one is much larger, and it supports both single phase and three phase AC inputs, and it incorporates a 2 kilowatt DC-DC converter to provide auxiliary power, similar to 7.2. It supports both EV charging in AC modes and as well as DC, and it's also available in 400 and 800 volt. Another product that is also launched is a 22 kilowatt onboard charger by the Zappi Group Thircom company. It's a 22 kilowatt, again available in 400 and 800 volt ranges. The interesting part about this product is actually the compact side, but also is the fact it's being bidirectional to support various applications, either like bidirectional to the grid or to the loads, or like different applications. So this can provide up to 22 kilowatts back in terms like from DC to EC. It supports the AC charging as well as DC charging, as well as it also supports the functional safety standards, just as ISO 26262 and DN 61508. It contains an enclosure that is IP6K9K. So, to end up this presentation, let's maybe summarize the key point that we discussed during this presentation. Extra low voltage below 120 volt powertrains architectures are very mature and contributed to substantial electrification penetration in various subcontract machinery applications. However, 400 and 600 volt powertrain are currently the voltage of choice for compact and mid-size mobile machinery. 800 volt architectures are emerging to provide the ultimate performance for heavy mobile machinery for electrification. The development of technology and components supporting high voltage powertrains is rapidly progressing. 7.2 kilowatt onboard chargers are becoming the standard for 400 volt systems, while 22 kilowatts are becoming the standard for 650 to 800 volts. OEMs looking to electrify heavy machinery, you need to consider many aspects related to the system architecture, design, components availability, safety, regulatory reliability, and service. The Staffy Group provide a comprehensive portfolio of high voltage solutions supporting the electrifications of off-road machinery. And with that, we conclude the presentation and open the floor for questions.
Thank you so much, Murad. We do have a few questions here from our audience. So there are two regarding the DC fast charging that I think I can combine. So the first one is, do you see DC fast charging becoming the standard across all heavy duty equipment? And the other one is, with the spread of fast DC charging, will the onboard AC chargers becomes unnecessary?
Yeah, thank you. So that's a good question, and that's a comment actually I have been hearing often from uh, different uh, development teams that are working on this project. Well, so the DC fast charging is important to support the applications of on of highway vehicles to allow for uh, charging during during the time of usage of the machine. So, for example, if there is a little break of 20 minutes or 30 minutes or a lunch break, that time could be used to actually recharge, like charge the vehicle and allow it to extend for the rest of the day. However, DC fast charging will not replace AC charging that is typically on board the vehicles for the foreseeable future, at least with the current chemistries that are used for batteries. And the reason why, so the fast charging is very fast, and typically the batteries are charged only from like 20 to 80%. So the DC charging is not used to actually go above 80%. Additionally, the fast charging is very, affect actually the lifetime of the battery. So it should be used with care, not like as the standard method. And like overnight, an easy slow charge is the best for the battery to ensure actually longevity at the battery, as well as most battery technologies, most battery packs, they require equalization and stabilization, which cannot be done when doing the DC fast charging. So the short answer is the EC um, charger, like AC to DC charger, it's still necessary to have on a vehicle, but it could be complemented during like the workday of the machine to have quick chargers for the machine to ensure like to be able to reduce battery pad and ensure longer runtime.
Okay. One more. What do you see as the tipping point for high voltage systems becoming standard in off-highway vehicles? Which industry will adopt high power charging the fastest? Construction, agriculture, material handling, and why?
Yes, good question. So um, all these industries would need high voltage chargers, but more particularly, the bigger the equipment, the more actually that's the only way to actually electrify some of this equipment. So, for example, agriculture. Like most applications, like if we exclude, for example, compact tractors and light duty equipment, the main in terms of numbers, the main segment in the agriculture is the agricultural structure, and that cannot like it's not practical to do it with low voltage. It has to be high voltage. However, in terms of adoption, agriculture is a little bit lagging behind other industries, so there will be a little bit the progression of electrification there will be a little bit delayed compared to other fields such as, for example, construction. Construction equipment are there is a lot of variety, and we have shown, for example, the previous slides some of like many of the systems that are actually showcased by the different vendors. So every OEM that I know of, every major OEMs has now product line that are electric. So in terms of timeline, I do see material handling is already highly electrified. I believe that more than 85% of the equipment, new equipment that is produced today globally is already electric. So only 15 is combustion engine, and that this proportion is actually decreasing. The second, the next sector that actually adopted this is construction, and agriculture will be lagging a little bit behind.
Thank you, Murad. We have a few more. The next one is regarding sustainability. Beyond efficiency, what are the real sustainability gains when moving to high voltage systems?
Yeah, sustainability. So, well, first of all, there are some systems like the large system. It's impractical to do them with low voltage. So the only solution is to do them with high voltage. So that's a necessity. The second thing is with high voltage, it's higher in efficiency. And now the good news is that the um, the silicons, the semiconductors uh, costs, like such as silicon carbides, their costs are going down. So in the midterm and the long term, the system will be more cost efficient. So beyond actually sustainability, which is important. There is also the regulatory, uh, like the regulatory uh, government, which is a little bit slowing down now. But we expect but I think this is we believe it's only temporary, and that like there will be more regulation actually to curb the emissions, the carbon emissions. Beyond that, there is real benefit of electrification. One of them is actually it allows to have autonomy and also automation of the vehicles, which are important factors in a lot of this field. It's not a surprise or it's not a secret that many in the agriculture field and the construction are now finding it more challenging to find the proper um, uh, operators for this machine, qualified operator for this machine. So they are what relying on autonomy and autonomous systems or partial autonomy and autonomous systems to help with that. And electrification actually enables that. The other aspect is actually like this beyond the pollution is actually noise pollution. So with electrification, you will allow to actually use the machines in different environments at night, in dense residential areas. Uh, and so it's a lot of benefit. And we do see, and everyone agrees that in the mid and long term uh, point of view, electrification will be predominant, will be available. Of course, it would not be the only thing. There are other optional things, especially for very large equipment, such as hybrid systems, such as using hydrogen or fuel cells. But it will be the predominant in mid, um, mid-size and large equipment. The extra large equipment may have different approaches to decarbonization rather than electrification.
Thank you, Murad. Now I have a question regarding the products that you just shared on your presentation. Why is the Zap Group launching two different 22 kilowatt onboard chargers?
Yeah. So these two chargers have commonality is actually the power level available, and they will be available both to support three phase and single phase. So they are meant for global use. Uh, Two key differences between the two products and which make them suitable for different type of applications. So the first one that is launched by Delta Q, it's unidirectional because I think in a lot of application construction equipment, bidirectional, like basically bidirectional vehicle like tied to the grid or is not a very, I would say, practical thing because the machines are being used when actually the grid need the, the power to transfer. So it doesn't make sense to have a machine and then use it for giving power back to the grid. So the business case and like, to use. bidirectional in lots of application is not really relevant. So unidirectional is fine, as well as this product will have an incorporated DC-DC converter. However, in certain particular applications that they would need great time, the second product is fully bidirectional, and it's very compact, as well as it has some of the functional safety. It's compliant with some of the functional safety that may be required by some OEM. So the two products are similar in power, however, the feature set are very different.
Perfect. And we have time for one final question. Are you experiencing off-highway vehicle OEMs scaling back on electrification?
It's not a secret. Like I've been attending like a few of the international for several years, the major exhibitions and talking to OEMs. So there is definitely last year and this year a little bit of softening of the demand for electrical vehicles, but this softening it's only temporary. All the people we talk to is like they say in the midterm and long term, electrification is growing. There is a little bit softening because of the geopolitical situations, because of the economical conditions, but the industry is going strong into electrification. And one of the major hurdles actually for adopting battery powered and electrical systems is actually the cost uh, of the machine versus a combustion engine, a traditional combustion engine, where that gap is progressively narrowing to the point where actually, I believe in China, uh, they are able to get electric loaders, in the field of loaders, the cost of an electric loader machine is actually now not only similar but lower than equivalent of diesel machine. So yes, we are not there yet, but the gap in terms of cost is narrowing down, and you have all these advantages that are coming with electrification, including lower total cost of ownership. The major hurdle now is the initial cost, but I think that's becoming becoming lower. So in the midterm and the long term, it's electrification is going strong. There may be some slowdown as we have seen recently, but that doesn't change the long term forecast.
Perfect, Murad. Thank you again for this amazing session. Thank you, everyone who joined us today. We still have a few sessions left for today, and we have the full day tomorrow for lots of sessions. Make sure to register. And we also, this year, we have the news, right, that we have the certificate of attendance for continuing professional development. So everybody who attended the session will get the certificate. And again, thanks again, Murad, and make sure to join the next sessions from the lobby. Bye bye, everyone. It was a pleasure to be your host today for this session. Bye. Have a great day.
Thank you. Bye bye.